In this video you will learn what a current divider circuit is and according to which rules the electric current is divided at a branch in a circuit. You will learn that there are two variants of the current divider rule and that you have to decide which variant to use depending on the given and required quantities which you find. And by the end of this video you will be able to calculate missing currents in your circuits quickly and easily. And finally, as always, there's going to be a summary of the most important facts for you at the end of the video, so stay tuned. And my name is Andreas from The Fearless Engineer, and here we go. In this video we're going to talk about the current divider rule, and before we dive into the details, let's briefly discuss a broader definition of this concept. And if you look it up on Wikipedia, you will find that it says there that in electronics a current divider is a simple linear circuit that produces an output current that is a fraction of the input current. And current division refers to the splitting of current between the branches of the divider. So it's about splitting currents on certain points in a circuit. The current enters this point, the current is split up into several branches, into several sub-parts of the circuit, and we want to know the ratio of this splitting up of current depending on what's happening inside these individual branches. So we can exactly know by looking at the resistors in this case, which is what's the driving force behind this forming of split up ratios. We want to know which fraction of current goes into which branch. That's the aim of the current divider. And before we dive into this concept, let's quickly recap some items which we need from previous videos in order to progress here. And the first is that Kirchhoff's first rule states that at a junction in a circuit, the sum of the inflowing and the outflowing currents is always zero. This is basically the conservation of charges within a circuit. Charges are never lost. When they enter a junction point, you have the same charges leaving the junction point. They are identical to the charges which have been previously entering the junction point from inlets, so to speak, of the circuit. And the sum of from the charges entering and the sum of the charges leaving is always identical, and the difference between the two is then zero. The second point here, the second key aspect, is that the voltage drop across resistors which are connected in parallel is always the same, because the potentials above and below are the same for the components. If you recall the definition of voltage, voltage always refers to a difference in potential, identical to, let's say, the gravitational field of the Earth, which produces a potential energy of an object in a certain height above ground, which has a certain mass. And basically, the conversion of potential energy from one position, let's say an apple hanging in 2 meters, to the same apple hanging in 1 meter, this difference in potential energy, this can be very well, in a very good manner, compared to voltage. Voltage refers to the difference in potential energy between 2 points. And this is the basis, these two items, for understanding and deriving even the current divider. Let's take a look at an example of the current divider. This is an example which has a voltage source on the left, 10 volts, and we have a junction point here which splits up the current into a left branch and a right branch. And if you look at the resistor values inside the branches, we have a resistor R1 in the left branch which has 100 ohms and a resistor in the right branch which has 4 times the resistance value, 400 ohms. And if you take a look at the currents, we have 100 milliamps entering the left branch, 25 milliamps entering the right branch. The sum of these two currents is identical to the total current which has entered the branch coming from the power source. And if you take a look at the values here, 100 milliamps enters the 100 ohm branch, and a fourth of this current enters the right branch, which leads to the second resistor, which is 4 times as large as the left one. So this 25 milliamps corresponds to the 400 ohm branch, and the 100 milliamps corresponds to the 100 milliamps branch. And you can see here that the current through the branch with a smaller resistance is driven by the ratio of the resistors to each other. This one is, or the inverse of this. This one is 4 times as high as the resistor on the left, and the current entering this node is 4 times as low as the current entering the left branch. Well, let's take a look at the first variant of the current divider rule. In this video, we're not going to derive the rule yet. This is something which we are going to do in the next video. In this video here, we're going to look at the formula without knowing yet where it comes from. If you look at the small circuit here on the right-hand side, you can see that we have a total amount of current entering a top junction point, and this is given to us. We know this value here. Also, we know the different resistor values. We know R1, we know R2. We do not know I2. This is a current which is unknown to us, and we are looking for the current I1. And we can compute I1 given these green values here by using this formula. So I1 is the product of the total current entering the node, this node where the current branches into two parts, and the ratio of R2, which is the resistor value inside the other branch, which is not the one we are looking for. So R2 is the resistor value in the branch opposite to the current we are looking for, and by the resistance values below the fraction line here is the sum of the two resistors here, R1 plus R2. So this is the formula which we are going to use for the first current divider rule, given this configuration here. And on this slide, you can see the second possible configuration. We do not have the total current right now in this scenario here. We still have the resistance values R1 and R2, but we now have this second current I2, and we are still looking for the current I1. So given this scenario here, we can use this variant of the current divider rule, which tells us that the current I1 we are looking for is the product of the current in the opposite branch multiplied with a ratio of resistance value in the opposite branch divided by the resistance value in the branch with the current we are looking for. So this formula needs to be applied for such a configuration here if we do not have the total amount of current given. Let's quickly summarize the most important takeaways from this video here. Firstly, the current divider rule can be used to calculate the ratio in which the current is divided at a branch in a circuit. Then secondly, depending on the given and sought after quantities in your equations, it is necessary to use the appropriate variant of the current divider rule in each case. And lastly, the derivation of the two current divider rules which we have seen here is possible with the help of the voltage equality for parallel components, Kirchhoff's junction theorem, and Ohm's law, which is something which we will take a look at in depth in the upcoming next video. That's all from me for now. If you have any questions, drop them in the comment section down below. Also, ideas for future videos should go there. And that's all from me for you for today. I wish you a nice day. See you next time here on The Fearless Engineer.